Friends, welcome to the tutorial series on network analysis made simple. This is a module-wise electric circuit analysis paper solution series. In this tutorial, we are going to solve VTU CBCS scheme electric circuit analysis paper of December 2017, January 2018, module 3 of syllabus 15E32. Friends, I prefer to emphasize on basic circuit concepts, strategy and thinking process rather than detailed mathematical steps. I am sure you are already well equipped with the relevant mathematical skills required. Hope this tutorial ignites some of your thoughts. Let's go ahead. Friends, first we are going to answer question 1, which states like this. What are the initial conditions and their use in network analysis? Friends, you all know that electrical networks are subjected to switching. Switching could be a manual activity or could be an event when fault occurs. During the instant of switching, the network elements, particularly the energy storing elements such as inductance and capacitance, behave differently. Inductance is a current sensitive element and it opposes the rate of change of current, and capacitance is a voltage sensitive element and it opposes the rate of change in voltage. During the instant of switching, the current through the inductance and the voltage across the capacitor present are called as initial conditions. For example, if the switching takes place at t is equal to 0, the current through the inductance IL0 minus and the voltage across the capacitor Vc0 minus are known as initial conditions. Friends, next we shall state the uses of the initial conditions. In the first place, initial conditions are useful in evaluating arbitrary constants that appear in the general solution of differential equations. They provide the knowledge of the behavior of the network elements at the instant of switching. They are also useful to study the transient performance of electrical networks. For example, if IL0 minus is equal to 0 and if it is switched at t is equal to 0, then at t is equal to 0 plus, it behaves as open circuit. Similarly, if Vc0 minus across the capacitor is 0, at t is equal to 0 plus, it behaves as a short circuit. If IL0 minus is present, inductance will behave as a current source, and if Vc0 minus is present across the capacitor, it will behave as a voltage source at t is equal to 0 plus. Hope it is clear to you. Friends, next we shall answer question 2. In this question, we are required to just write the equivalent circuits for R, L and C circuit elements. 1 at t is equal to 0 plus and 2 at t is equal to infinity. The equivalent circuits for R, L and C at t is equal to 0 plus and at t is equal to infinity are represented in the table shown. But for your benefit, let me explain the meaning of the equivalent circuits. We know the resistance circuit element follows Ohm's law and hence it will not change its status at t is equal to 0 plus and at t is equal to infinity as shown. If IL0 minus is equal to 0, then at t is equal to 0 plus also IL0 plus is 0. So, a zero current implies open circuit and hence at t is equal to 0 plus inductance behaves as open circuit. At t is equal to infinity, IL becomes constant. So, di by dt is equal to 0. Hence, voltage across the inductance L into di by dt is equal to 0. So, a zero voltage implies short circuit. Similarly, if Vc0 minus is equal to 0, then Vc0 plus also will be equal to 0. So, a zero voltage implies short circuit. Capacitor is fully charged at t is equal to infinity and Vc becomes constant. So, C into dV by dt will be equal to 0. Hence, zero current implies open circuit. On the other hand, if IL0 minus is equal to I0, inductance will behave as a current source, and if VC0 minus is equal to V0, capacitance will behave as a voltage source as shown. Hope it is clear to you. Friends, next we shall solve question 3. In this question, we are required to find I0 plus di by dt 0 plus and dt squared I by dt square 0 plus in the circuit shown in figure. It is given that the capacitor is initially uncharged, meaning Vc0 plus is equal to 0. Friends, at t is equal to 0 plus, the switch K is closed, C is short. Incorporating these aspects, the equivalent circuit at t is equal to 0 plus drawn is shown in figure. Observe the network. We find that I0 plus is equal to 100 divided by 1000 equal to 0.1 amperes. We have got one answer already. To find di by dt 0 plus and d squared I by dt square 0 plus, the circuit for t greater than or equal to 0 drawn is shown in figure. By writing the loop equation in terms of instantaneous values, we get R into I plus 1 upon C into integration I dt is equal to V. By differentiating it, we get R into di by dt plus I by C is equal to 0. By substituting for time t is equal to 0 plus, we get equation 1. Friends, by substituting R is equal to 1000 ohm and C is equal to 1 microfarad, I0 plus is equal to 0.1 amperes and solving, we get di by dt 0 plus is equal to minus 100 amperes per second. To find d squared I by dt square 0 plus, by differentiating equation 1, we get R into d squared I by dt square 0 plus 1 upon C into di by dt 0 plus is equal to 0. By substituting the values and solving it, we get d squared I by dt square 0 plus is equal to 10 to the power of 5 amperes per second square. Hope it is clear to you. Friends, next we shall solve question 4. In this question, we are required to find I0 plus, di by dt 0 plus and d squared I by dt square 0 plus when the switch is moved from position A to position B at t is equal to 0. It is given that the circuit has reached the steady state when the switch is at position A, meaning at t is equal to 0 minus, the circuit elements will behave as though they are at t is equal to infinity. Therefore, at t is equal to 0 minus, the switch is in position A, L is short and C is open. Incorporating these aspects, the equivalent circuit at t is equal to 0 minus drawn is shown in figure. We find that I0 minus is equal to 100 divided by 1000 and that is equal to 0.1 amperes. Also, IL0 minus is equal to IL0 plus is equal to 0.1 amperes. Further, Vc0 minus is equal to Vc0 plus is equal to 0 since the circuit is open. But friends, at t is equal to 0 plus, the switch is at position B, L is open and C is short and the inductance will behave as a current source of 0.1 amperes as shown. So, I0 plus is equal to 0.1 amperes. We have got one answer. To find di by dt 0 plus and d squared I by dt square 0 plus, the circuit drawn at t is equal to 0 plus is shown in figure. By writing the loop equation in terms of instantaneous values, we get R into I0 plus L into di by dt 0 plus 1 upon C into integration I0 plus dt is equal to 0. But we know 1 upon C into integration I0 plus dt is equal to Vc0 plus and Vc0 plus is equal to 0. That we know. By substituting the values and solving, we get di by dt 0 plus is equal to minus 100 amperes per second. To find d squared I by dt square 0 plus, by differentiating equation 1, we get R into di by dt 0 plus L into d squared I by dt square 0 plus I0 plus divided by C is equal to 0. By substituting the values and solving, we get d squared I by dt square 0 plus is equal to minus 9 into 10 to the power of 5 amperes per second square. It's very easy, isn't it, friends? Friends, next we shall solve question 5. In this question, we are required to solve for V0 plus dV by dt 0 plus and d squared V by dt square 0 plus in the circuit shown in figure. It is given that the switch K is opened at t is equal to 0. Note that. Meaning, it has remained closed for a long time or for an infinite time. So, at t is equal to 0 minus K is closed, L is short. Incorporating these aspects, the equivalent circuit at t is equal to 0 minus drawn is shown in figure. Observe the network. We find that V0 minus is equal to 0 since L is short. Also, IL0 minus is equal to IL0 plus is equal to 0. But friends, at t is equal to 0 plus, K is open, L is open. The equivalent circuit at t is equal to 0 plus drawn is shown in figure. Now, 1 ampere current will flow through 100 ohm. So, V0 plus is equal to 100 volts. We have got one answer. To find dV by dt 0 plus and d squared V by dt square 0 plus, the circuit for t greater than or equal to 0 drawn is shown in figure. Observe the network. By writing the nodal equation for node V, we get V divided by R plus 1 upon L into integration V dt minus 1 is equal to 0. At t is equal to 0 plus, we have V0 plus divided by R plus 1 upon L into integration V0 plus dt is equal to 1. By differentiating equation 1, we get 1 upon R into dV by dt 0 plus 1 upon L into V0 plus is equal to 0. By substituting the values, R is equal to 100 ohm, L is equal to 1 Henry, V0 plus is equal to 100 volts and solving, we get dV by dt 0 plus is equal to minus 10 to the power of 4 volts per second. To find d squared V by dt square 0 plus, by differentiating equation 2, we get 1 upon R into d squared V by dt square 0 plus 1 upon L into dV by dt 0 plus is equal to 0. By substituting the values and solving, we get d squared V by dt square 0 plus is equal to 10 to the power of 6 volts per second square. Friends, For strengthening your basic concepts and developing your thinking process, I suggest you refer my textbooks titled Network Analysis Made Easy, Basic Electrical Engineering, Basic Electronics, and Linear Integrated Circuits and Applications, which are available online. Thank you for watching this video.